Assalamualaikum warahmatullahi wabarakatuh. My name is Icha Khairani with my student ID 24109310009. Now, I will explain about the linear programming in Operational Research 1 in Module 1. Next, the definition of the linear programming is linear programming, or LP, is a mathematical technique used to allocate limited resources among competing activities in order to achieve the best or optimal outcome or solution. The term linear means that all mathematical functions in the model must be linear, or no exponent and no multiplication between variables. The term programming in this context refers to planning. The objectives of the linear programming is to maximize the profit, revenue, or efficiency, and to minimize cost, distance, or time. The four basic assumptions for linear programming is first, proportionality. The output and resource usage proportionally with activity level. Second is additivity. The total result is the sum of individual contributions or no interaction between variables. The third is divisibility. Decision variables can take fractional value or are not restricted to integers. The last is certainty. All parameters are known and constant or no uncertainty. Next is integer linear programming. The integer linear programming, or ILP, is an extension of linear programming where one or more decision variables must be integers. ILP is used when decision variables represent indivisible quantities such as number of people, number of machines, number of vehicles, and yes or no decision, or 0 or 1. ILP is important because without integer constraints, LP solutions may result in unrealistic fractional value. For example, an LP solution may suggest producing 3.0 cars, which is not possible in reality. ILP ensures that the solution consists of whole numbers or integers. The types of the integer linear programming, the first is pure integer programming. Pure integer programming is all decision variables must be integers and no fractional values allowed. For the example, x1 equal to number of workers, or x2 is equal to number of machines. 2. Mixed integer programming, or MIP. MIP is some variables are integers and others can be continuous or fractions allowed. For the example, x1 is equal to number of factories or integer, and for the x2 is equal to production level. That production level is continuous. And the third is binary integer programming, or by IP. By IP is variables can only be 0 or 1 and used for yes or no decisions. For example, x1 is equal to build factory. The build factory is if 1 is equal to yes and 0 is equal to no. The applications of BIP is for the investment decisions, facility and location selection, scheduling, and routing problems. The component of the linear programming, the first is decision variable. Decision variables is the variables that represent the decision to be determined in a problem. They are usually denoted as x1, x2 until xn. For the example, x1 is equal to number of product A produced, and for x2 is equal to number of product B produced. The objective function denoted as z is equal to c1 x1 plus c2 x2 until the cn xn. The z is objective value, the xj is decision variables, and the cj is coefficient of each variable. Next is constraints. Constraints are limitations that restrict the value of decision variables. They represent real-world limitations such as raw materials, labor, or machine capacity. The constraints denoted as A11 x1 plus A12 x2 until the A1 n xn is less and equal to Bi. The Aij is equal to resource usage per unit, the xj is equal to decision variables, and the Ba is equal to the total available resource. Next, the non-negativity. Non-negativity constraint means that all decision variables must be greater than or equal to 0 because production quantity and resource cannot be negative. Next is the parameters. Parameters are known constant value used in a model. In linear programming, there are parameters like Cj equal to coefficients in the objective function, Aij is equal to coefficients in the constraints, and the Ba is equal to right-hand side value or research limits. The standard form of the linear programming. In the simplex method, all constraints must be in the form of equations or equal, and all variables must be more than equal to 0. Therefore, the model must be converted by adding variables. First, the slug or positive S for less than equal to constraints represents unused capacity. The surplus or negative S plus artificial for more than equal to constraints. Next, the artificial for equal constraints. The goal is to obtain an initial feasible solution before performing simplex iteration. We can see like this. Next, the types of solutions. First, the optimal solutions. An optimal solution is a feasible solution that provides the best value of the objective function, either maximum or minimum, depending on the problem. The optimal solution is divided into two types. The first is unique optimal solution. Unique optimal solution occurs when there is only one combination of decision variables that produce the best objective value. This is the most common case in linear programming. The characteristics of a unique optimal solution is only one best solution occurs at a single corner point and no other solution has the same objective value. Next is the multiple optimal solution. The multiple optimal solutions occur when more than one feasible solution produce the same optimal objective value. This means there are several equally optimal decisions. Multiple optimal solution. The characteristics of the function is parallel to a constraint. Infinite optimal solutions along a line. All points on the line give the same value. Two is unbounded solution. An unbounded solution occurs when the objective function value can increase or decrease indefinitely without violating any constraints. This usually indicates that the model lacks sufficient constraint. The characteristics of the unbounded solution is feasible region is open, no constraint limits the optimization direction, and no optimal solution can be found. The study case of the linear programming is the winner Glasgow is a manufacturing company that produces two types of products, glass doors for product 1 and windows for product 2. The production process is carried out in three plants, each with limited production capacity per week. Each product requires a different amount of processing time in each plant, and each product generates a different profit per batch. Given these capacity limitations, the company aims to determine the optimal number of batches for each product in order to maximize total profit. This is the production data of the company. From the data, we get the mathematical model. For the decision variables, the x1 equal to number of batch of product 1 and for x2 is equal to number of batch of product 2. The objective function is to maximize the profit. So the objective function is 3x1 plus 5x2. The constraints from the plan is for the plan 1 is x1 is less and equal 4. For plan 2 is 2x2 is less than equal to 12. And for the plan 3 is 3x1 plus 2x2 is less than equal to 18. And for the non-negativity constraint is x1 and x2 is more than equal to 0. From the case and the mathematical model, we use the graphical method and we make the graphic from the constraint and we get the feasible region and the corner point of the feasible region. After that, we get the solution. The optimal solution is found at the intersection of constraint. The result is x1 is equal to 2 batches and for x2 is equal to 6 batches. The maximum profit is equal to 36. The competition is the company should produce 2 batches of glass doors and 6 batches of windows to achieve a maximum profit of $36,000 per week. So that's all for my presentation. Sorry if I have made any mistake. Thank you. Assalamualaikum warahmatullahi wabarakatuh.